Hello, physical science folks. We are at the start of our last unit for the semester, which is thermochemistry, talking about heat and heat transfer. And today we have been talking about and will continue to talk about a big idea this unit called heating and cooling curves. This is going to ask you to use some of your graphing skills and to take a look at what happens as we put energy in or take energy out of a material and as it goes through different phase changes as well. To start off, look at this graph. It is very basic. It does not provide a whole lot of detail for you. As a matter of fact, over here on the y-axis, we have temperature in Celsius. We don't have any numbers. We just know that as you go higher on this axis, that means that the temperature is getting hotter and hotter and hotter. Okay? And time runs across the x-axis down here on the bottom. We don't have specific numbers. We just know that time ticks away independent of any other variable. All right? What you're looking at here is the temperature of some material as time ticks away and as we continue to heat it up. All right? And a couple things I want you to notice. This graph does not even identify what we are heating up, right? This could be water. This could be motor oil. It could be gummy bears, right? We don't identify it, and that is on purpose. We want you to see the pattern first before you worry about what's actually happening. All right, so I want to point out a couple of things to you. Notice that at the beginning part of this graph, we use these letters to help us divide the graph up into segments. Okay, so A is not this section. A is the beginning point, and B is this point right here. So we could talk about this segment of the graph as AB, or from A to B. Notice that as time ticks away, the temperature of this material is increasing, right? It's getting hotter and hotter and hotter. But then all of a sudden, something mysterious happens. Between B and C, time keeps ticking away, but notice that the temperature holds constant. It doesn't heat up and it doesn't cool down. Then, for some reason, from C to D, time keeps ticking away and the temperature starts to increase again, getting hotter than it was before until it reaches this section up here, which is D. And from D to E, again, we have this plateau or flat part of the graph where time keeps ticking away. Heat continues to be put into the substance, but the temperature doesn't change, right? How in the world could that be? How could we put thermal energy into an object, but have the temperature not actually rise? And the last segment of the graph here, from E to F, we see that all of a sudden the temperature begins to increase again as time ticks away. So what in the world is going on here? This is called a heating curve. And I realize that you might think it doesn't really look like a curve. Well, we've oversimplified it. This pattern is what happens with materials in the real world. By the time you're watching this, you probably have already seen us heat ice in the classroom and take it from a from a solid to a liquid, and then from a liquid into a gas. And so parts of this graph, if not most of the graph, should look familiar to you based on the lab that we've already done. Let me move you along to the last slide here real quick. This is now the same heating curve, but it shows a little bit more detail, okay? We still don't have a whole lot of temperatures over here on the side, but we do have some. We have negative 40 degrees, this is in Celsius, 0 degrees Celsius, 100 degrees Celsius, up to 130 degrees Celsius. Okay, time across the bottom has not been labeled, and that's because we don't know what is heating this liquid up. Let's just pretend that it's water. It's good old-fashioned H2O. Watch what happens now. When we start off at the beginning from negative 40 to 0 degrees Celsius, this water is in solid form. We call that ice, right? No duh. Look at the very top here. This represents the molecules in that ice. They're locked together in place. You can't see, but they're vibrating a little bit. But they're not really moving around with respect to each other. They're locked in place, and that is a solid. But magically, if you heat up that solid enough, when it gets to 0 degrees Celsius, that is what we call the melting point. And the melting point for water is when it starts to go from a solid into a liquid. This would be a time when we would have liquid and ice in the same container. Notice how some of the molecules start to break off. They start to be solid and a liquid at the same time, and those that are liquid have a little bit more movement, a little bit more energy, and they're able to move around with respect to each other. But notice, folks, that when that phase change is happening, when it's melting, the temperature does not change. The temperature holds constant. And that is because all of the energy, all of the thermal energy that we are putting into heating that substance up is going into breaking these intermolecular forces. Ooh, there's a big phrase. The intermolecular forces breaking a solid down and turning it into a liquid. That's where all of that energy is going. Now, as soon as it's melted, as soon as we have a liquid, look what happens to the temperature. The water can begin to heat up from 0 degrees Celsius all the way up to 100 degrees Celsius. During that time, these molecules are moving around faster and faster. They're flowing, they're moving. They still have intermolecular forces that are pulling them together, okay? But if we get it hot enough, what happens is that liquid starts to turn into a gas. And those molecules now move even further apart, and they move even faster, and they have a huge range of motion. And during this time, we have a liquid that's turning into a gas, okay? Could be considered evaporation or vaporization because we're putting so much thermal energy into this phase change. But notice, phase change, the temperature levels off, and it does not increase and it does not decrease, doesn't heat up and doesn't cool down until it is all a gas. As soon as that H2O is turned completely into a water vapor, then the gas can now be heated again to actually very, very dangerous temperatures. It does not stop at 130. It will continue off that chart and get incredibly, incredibly hot. All right, so this is a heating curve. When a phase change is happening, the temperature levels off. Okay, how do we know a phase change is happening? Because all the energy that's being put into this water is going into changing its phase from one state of matter to another state of matter. Okay, if the temperature is rising or falling, we know that a phase change is not taking place. Now here's the crazy part for your brain. Try and get ready for this one. This process can actually be reversed as well. Okay? The exact opposite can happen when we cool that object down. If we take vapor in the air and cool it down enough, a phase change will happen and it will go from gas into a liquid. Okay? The temperature levels off. We call that condensation. And once it's liquid water, it can be cooled down. The temperature can drop until it gets to 0 degrees Celsius, and then it starts to freeze. And during freezing, the temperature doesn't change, it holds constant. And then once you get ice, this blows some people's minds. Once it's solid ice, you can continue to lower the temperature of that ice. Not all ice is the same temperature. It can get colder and colder and colder, right? But remember, whether you're heating it up or cooling it down, if a phase change is happening, then the temperature levels off. Okay, you probably saw this in the lab today. If you haven't done the lab, go back and look at our data, and you'll see that a phase change actually causes the temperature to level off. All right, if you got questions, let me know what they are.